Hello, my name is John Lucero, and today we're going to take a look at Eulerian graphs and examine why they are of significant importance in the world of graph theory. We will review two of the most prominent examples, the Königsberg bridge problem and the Chinese postman problem. In the 18th century, there was an interesting problem that laid the foundation of a topic of mathematics that we now know as graph theory. In the country of Prussia, there was a town by the name of Königsberg, which was made up of 2 islands and 2 riverbanks. These 4 different landmasses were separated by the Prego River, and hence 7 bridges were built. The citizens of Königsberg who walked through the city would often have to cross one of the bridges to get to their destination. Some wondered if it was possible to cross each of the bridges only once during a single walk. Go ahead and try it out yourself. Are you having trouble? Let's try and use graph theory to figure out if there is a possible solution. In the context of graph theory, we can model this scenario as a graph where the landmasses can be represented as 4 vertices, denoted by A, B, C, and D. And the bridges can be represented as individual edges. A circuit C, where each edge of a graph G appears only once, is known as an Eulerian circuit, and any connected graph G that contains an Eulerian circuit is called an Eulerian graph. Why are these terms named Eulerian? Well, this problem became quite famous and eventually attracted the attention of Leonhard Euler, one of the greatest mathematicians of his time. After conducting his own research, he correctly observed that we should not look at the bridges themselves, but instead look at the landmasses, or vertices. Whenever a walker enters a bridge starting in one landmass, say A, they must exit that same bridge before they end up in a different landmass, say B, C, or D. In graph theory terms, if we want to establish an Eulerian circuit in the graph, then the number of times that a walker enters an initial or non-terminal vertex must be equal to the number of times that the walker leaves the same vertex and enters a different vertex. Therefore, we must consider the number of bridges that are linked to each of the landmasses, except for the landmasses where the path starts and finishes. For each of the remaining landmasses, the landmass must have an even number of linked bridges, or in graph theory terms, an even degree. Today, this represents one of the most important themes in graph theory. In this example, we observe that each of the landmasses have an odd degree. A has a degree of 5, while B, C, and D each have a degree of 3. Not counting the starting and ending vertices, there are at least 2 remaining vertices that both have an odd degree. Since we know that every time a path enters a vertex, there must be an exit path as well. And so we can state that these vertices must have an even degree in order to be considered an Eulerian graph. Thus, Euler was indeed right in determining that it was impossible to travel through each bridge in Königsberg only once in a single trip. Let's now take a look at another problem involving Eulerian graphs. In 1960, a Chinese mathematician named Quanmai Ko introduced a problem where a postman must deliver mail to all of the mailboxes within a neighborhood in the most efficient manner, meaning that he does not use the same path or edge more than once. Yes, this in fact would represent an Eulerian circuit. Let's use the following layout where a postman needs to travel to each of the 18 mailboxes placed on the side of a street. Can the postman make a successful round trip through the neighborhood and deliver mail to each mailbox without passing by each mailbox more than once? Go ahead and try your best to draw lines going through the layout to answer this question. Okay, let's solve it using graph theory. The first step we can do is identify what our vertices and edges will be. We can establish the street intersections as the vertices. Here we label them as A through K, and the streets with mailboxes represent the edges. So in total, we have 10 vertices and 18 edges. We can then use the theorem we mentioned in the Königsberg Bridge problem. The formal definition is as follows. A non-trivial connected graph G is Eulerian if and only if every vertex of G has even degree. By inspection, we can see that A has a degree of 2, B has a degree of 4, C has a degree of 2, D has a degree of 4, E has a degree of 4, F has a degree of 2, G has a degree of 4, H has a degree of 2, I has a degree of 4, J has a degree of 4, and K has a degree of 4. Since every vertex has an even degree, we know for sure that this problem contains an Eulerian graph. As such, we identify the following route. A, B, C, D, J, I, B, J, K, D, E, K, G, E, F, G, H, I, A satisfies this problem. So yes, a postman can in fact complete a route through the neighborhood and deliver mail to each mailbox, only passing through each mailbox exactly one time.